This question is taken from 2023 MIT Integration B final. Okay, let me do this one by using basic techniques integrations. And as I did in other videos, that I'm always using basic calculus integration techniques instead of using like Cauchy residual or Feynman tricks or Laplace transformation and so on. Now here I'm not using gamma function or beta function. I'm just using basic simple techniques of integrations like in substitution by parts, partial fractions, and so on. So this is a good example for those who are taking the basic calculus course. Now, the first step, this integral is equal from 0 to half pi. And the denominator, this is sine square plus cosine square plus 2 sine cosine. Therefore, this is equal to 1 plus 2 sine x cosine x, isn't it? On top is a cubic root tangent x. Now here I'm multiply the secant square both to the top and the bottom. Therefore, the equal sign is there, maintained. Now, something good here is that secant times 1 is secant square. Secant square is 1 over cosine square. So this over cosine square becomes tangent. So it becomes 2 tangent x. This is a cubic root tangent. This is the derivative of tangent, right? So everything almost in tangent. This could be 1 plus tangent square. So it is equal now from 0 to half pi. This is 1 plus tangent square plus 2 tangent. Therefore, the denominator is equal to 1 plus tangent x square, right? Correct. And then this is a cubic root tangent x and d tangent x. So here, clearly that I can bring new variable for tangent. Say, how about t? T is equal to tangent x. Therefore, my integral becomes cubic root t, right? And dt, 1 plus t square. Now the boundary has been changed. When x equal to 0 is 0. When x equal to half pi, this is infinity. So integral has been changed to this. Well, I think it's much better. Now, as I said in the beginning, that I'm using basic techniques of integrations. There's no sophisticated ones, or beta or gamma functions and so on. Here I'm using substitution. I want to get rid of the cubic root. So I let This is definite integral, okay? So therefore, those variables are just dummy variables. I can use x, can I? Why not? Let x be cube root t. Well, it doesn't matter. I can use u. I can use whatever it is, because this is definitely integral. Therefore, those variables are just dummy variables. Then t is equal to x cubed. Therefore, my integral has been changed to x and d x cubed, right? This is the 1 plus x cubed square. Yeah, that's right. Good. Now the boundary is not changed, 0 to infinity, because of this. Now, what am I doing then here, from here? Now look, this is 1 plus x cubed square. So I can write x cubed plus 1. There's no difference, right? Dx cubed is the same thing as dx cubed plus 1. Now something good for this is that I can write this over this. I can write a d 1 plus x cubed. Yeah. This one derivative is a negative 1 over this square multiplied by this derivative, which is this, right? So I need a negative. I put a negative outside. Then it's equal. Okay. Here I can use by parts. This is u, this is dv. So this is equal to negative uv. U is this. V is this. From 0 to infinity. Minus the v du. Minus become plus. Right? There are minus here. Negative infinity here. V du. V is this. 1 plus x cubed. Du is dx. Yeah. Now, when x is approaching to infinity, that is 0. When x is 0, this is 0. So this is 0. Therefore, my integral becomes this. So this is my new integral from the given integral. So that we are focusing this integral on. This is rather easy. Well, I shouldn't say rather easy, but rather simpler. This one is obviously by partial fractions, right? This one is equal to x plus 1 plus x squared minus x plus 1, right? To factorize this one. And the x, this is a, right? This is bx plus c. Partial fractions. Now, I just take time to do the finding those ABC, right? I suppose you know how to do the partial fractions. Now here, a is equal to 1/3. B is equal to negative 1/3. C is equal to 2/3, positive. Well, I'll leave it for yourself to fill up the details, right? Just determining ABC. So the first integral is very easy. A is 1/3. This is 1/3 log x plus 1, right? From 0 to infinity. That is this one. Now the second one is plus integral from 0 to infinity x squared minus x plus 1 negative 1/3 x plus 2/3 dx. Okay, now let me this look, how should I? Okay, now the denominator is this x squared minus x plus 1. I want to have this x squared minus x plus 1 and a d x squared minus x plus 1. This will end up with a log function, right? Natural log. It's very easy. This one is equal to x squared minus x plus 1. This will be 2x minus 1 and dx. So I need this. So I have this, which is equal to natural log x squared minus x plus 1. But at the same time that I must consider the given numerator, so the equal sign has to be maintained. So this is the way I'm doing. This is 1/3 natural log x plus 1 from 0 to infinity plus integral x squared minus x plus 1. Look, I want this. I want this, don't I? So I write 2x minus 1. This is what I want. So I can have this. But at the same time that I want to maintain an equal sign. And the result has to be this. Now, how do I change this one to this? I must be multiply negative 1/6, right? Negative 1/6. So I have a negative 1/3 x come back. Same time I have this positive 1/6. Positive 6, but actually 2/3. 2/3 is 4/6. This is 1/6. So I must be adding another half. Then is equal, right? Equal sign there. Dx. I hope everything is good. So this one becomes 1/3 natural log of x plus 1 from 0 to infinity. This part is equal 1/6 natural log x squared minus x plus 1. That is what I designed in the first place, right? Plus 1/2. Now this is from 0 to infinity, right? 1/2 integral from 0 to infinity. This dx. Now this integral, I need a complete square, right? As I said at the beginning that I'm dealing with the integrals with all basic techniques. This is x minus half square, right? And to maintain equal to 1, this is equal to 3/4. Yeah. You see, everything is equal. Now here, 2 logs, I can put them together. This is 2/6. 2/6. Therefore, this was equal to 1/6 is common. This is 2, right? X plus 1 square. This will be x squared minus x plus 1 from 0 to infinity. 2 over 6. 2 come here, 2 goes there. 6 combined with this is common factor. And plus 1/2 this integral from 0 to infinity. Now I need a basic formula. Basic formula is this, right? 1 over tangent square d this. That is basic formula. This is for arctangent this, right? Plus c. Now, so I need a 1 here. So I take 3/4 out. So this is 1, right? Plus 1. And at the same time, this becomes x minus half and 2 over root 3. Root 3 over 2 square in the dx, right? Yeah. Now this one, when you take limit, because the numerator and denominator both are second degree polynomial with the same coefficient and leading term, therefore this limit is 0. Now this limit is 1 rather when you take limit x goes to infinity, right? Yes, x go to 0 is 1. X go to infinity is also 1. Therefore log 1 is 0. So this one is 0. So this becomes 1/2 times, this is out, right? This is 2 over 3. Integral from 0 to infinity. And the denominator will be 2x plus 1 over root 3 square plus 1 after this, right? Yeah. And the dx, I can write d 2x plus 1 over root 3. And to balance for dx, I multiply root 3 over 2. So it is equal. So this one is equal to this is 4, right? I can write, sorry, this is 4. Yeah. So this is 1/2. This is 4 over 3 times root 3 over 2, and this is arctangent 2x minus 1. Sorry, this is always something minus 1 over root 3 from 0 to infinity. So I need a little more space. So this is 0. Now the result is well, this is root 3, right? Root 3. 4 cancel with 4, root 3, yes. Multiplied by arctangent infinity is a half pi minus when x equals to 0, this is a negative 1/3. Negative is a negative pi over 6 So this one equal to root 3. This is 4 over 6 part. The 3 over 6, 1 over 6, 4, yeah. So this one is equal to, well, I hate those calculations. This is 3 root 2, 3 pi. And multiply by root 3. So this one is equal to 9 over root 3 to root 3 pi, yeah. So that is the final result. 2 root 3 pi over 9. Bravo. Okay, so that is result. Okay, see, I got the answer for this integral without the sophisticated techniques as a beta function or gamma function. I'm using basic techniques. So this is a good example for students taking basic calculus course. You know, I'm using substitution, part by parts, partial fractions to get this very answer. Thank you.